everyone, and a very warm welcome. You are watching the 24th lecture in the series Mathematical Methods for Economics, and the topic we are currently covering in this series is differentiation. In the last couple of lectures, we had introduced the concept of a derivative. We had also talked about some simple rules for differentiation, such as the power rule, the product rule, and the quotient rule. And now in the lecture today, we will turn to some applications of derivatives, some economic applications, some economic interpretations of the idea of a rate of change. In particular, we will introduce in this video the idea of a proportional rate of change, which is actually a very important building block for formal academic discussions in the sciences, in the field of finance, and in economics as well. Also, if time permits, hopefully we'll have time in the end to also talk about higher order derivatives. So let's dive straight in and let's start talking about the proportional rate of change. Let us suppose we have a quantity y which is related to another quantity x through the function y equal to f of x. Okay? So given this function f of x, the proportional or the relative rate of change of the function at the point x equal to a is defined as f prime at a, that is the first derivative of the function at x equal to a, divided by the value of the function at a, which is f of a. So the proportional or the relative rate of change of the function at x equal to a is defined as f prime at a divided by f of a. And in general, if I were to just talk of the function f of x and I were not evaluating it at a particular point x equal to a, and we weren't interested in a particular point as such, in general, the proportional or the relative rate of change is given by 1 by y dy by dx. So in the numerator, you would have f prime of x, which is nothing but dy by dx, and that would be divided by y. Now here, some of you might already be asking questions like, why are we calling this a proportional or a relative rate of change? Why the word relative? Or one could even ask, what would be the, how exactly are you getting it, and how is it related to what we do in practice? So all of these questions we will be addressing in today's lecture, and we'll in particular be relating this to the rate of growth. So it'll be one thing at a time, and for this please bear with me. I will first set up the definition, and then I will move on to other details in this lecture. Okay, so this is as far as the proportional or the relative rate of change is concerned, the definition. And as I said, I've already given you a hint that, and also because this lecture is related to applications, the particular application I'm considering is a rate of growth. So I've already given you a hint that I will be linking this up with a rate of growth, with the concept of the rate of growth. So what I'm going to do is I'm going to tweak this function a little bit, and let's suppose that y is a function of time. Okay, so we are looking at time here as the independent variable, and that is basically because that will matter for us when we bring in the rate of growth. So when y is equal to f of t, the proportional rate of growth is defined as f prime of t, please see where my cursor is, f prime of t divided by f of t. Now this is nothing but dy by dt divided by y, which is what I have here on the right. So in the numerator we'll have dy by dt, and that will be divided by y. And if we use the dot notation, this can alternatively also be written as y dot by y. Whenever we put a dot on top of a variable, that indicates that we are taking the derivative of this variable with respect to time. So please note this particular notation, and this is something which we'll be using quite a bit whenever we take derivatives with respect to time. So basically, when y is a function of time, the proportional rate of change is 1 by y dy by dt or y dot by y. Note here that a proportional rate of change is usually quoted in percentages. So when time is, because here we are taking time as the independent variable, when time is the independent variable in particular, proportional rates of change are quoted as in percentages per year. And to illustrate, let us suppose the proportional rate of change for a variable is 4 by 100 each year. Then we say that the variable in question is increasing at 4% per year. Okay, so if the proportional rate of change for a variable is 4 by 100 each year, it is quoted as a percentage. So that is to say the variable is increasing at 4% per year. So this is something which you have to take note of in terms of how we report this particular rate of change. Now, just as an aside, there are some of you here, some of the viewers here might already be at a more advanced level, and they may have already done a course in calculus. So just as an aside, note that the proportional rate of change, which is 1 by y dy by dt, is nothing but the derivative of log, natural log y with respect to time. So if I take, for those of you who are familiar with this, with the differentiation for log functions, the derivatives of log functions, you would know that the derivative for ln y with respect to time is 1 by y dy by dt, and this is the expression for a proportional rate of change. And for those of you who are not yet at an advanced level in calculus, who have not done calculus in any other course, you can just hold on to this until we cover logarithmic functions later. Also, for students who have studied economics in high school or who have done an introductory course in macroeconomics, you must be used to calculating growth rates in economics. In fact, the expression that we have given you here, let me just go back to the previous slide, the expression for a proportional rate of change, which is y dot by y, this is actually nothing but a rate of growth. Growth rates are used throughout in the sciences, in the field of finance and in economics as well, as I mentioned in the beginning of this lecture. And there are various measures of growth rates that are used in economics. In fact, in economics, for instance, we calculate the rate of growth of output, the rate of growth of GDP, or it could be the rate of growth of total revenue for a firm, which we'll be looking at in a bit. Then you could calculate an inflation rate, which is the rate at which the price level changes. This is also a growth rate. So, for example, if we say that the inflation rate is 3%, this is to say that the price level is increasing at a rate of 3% per period of time. Then we could also calculate, we could look at population growth rates in economics or the rate of growth of capital stock. There are innumerable examples that one could cite here. But let us just pause for a moment. Till now, we have actually introduced quite a few terms. So what I would like to do is, I would like to tie all these together. We have talked about an average rate of change, we have talked about an instantaneous rate of change, and now we are introducing what is known as the proportional or the relative rate of change. So let's just see how all of these concepts connect with each other. Let me just make the terminology and the corresponding formulas very clear. And we'll do this with the help of an example. In this case, we'll take K of t, which is the stock of capital in an economy at time t. And with reference to this, I'll just give you the formulas for all the rates of change that we have looked at so far. Now, with K of t being the stock of capital in an economy at time t, let us suppose t increases to t plus h. Then the change in the capital stock is given by K of t plus h minus K of t. So this is the absolute change in the capital stock between time periods t plus h and t. Here the time span we are covering is h, and the average rate of change is then defined as K of t plus h minus K of t divided by h. We are averaging the entire change that we have in the numerator over that time span h. So that is the average rate of change. The instantaneous rate of change, which is nothing but our derivative, that is the limit as h tends to 0 of K of t plus h minus K of t, the capital stock at t plus h minus capital stock at time period t divided by h. So you take the limit of this ratio as h tends to 0. Basically, we are talking of just infinitesimally small increments in the time variable, and that then gives us the derivative of k with respect to t. And because it's a derivative with respect to time, we can also write dk by dt as k dot. So this instantaneous rate of change is nothing but the rate of change in the capital stock at time t. If we were to interpret it in words, if we were to interpret the derivative in words, this expression k dot is nothing but the rate of change in the capital stock at time t. Now, the proportional rate of change, which we are going to introduce as a rate of growth, that is given by k dot by k. That is also rate of growth. So, the question now is, let me just give you some more details here. How do we move? So, if we are starting with the instantaneous rate of change, which is k dot, and now I want to move to the proportional rate of change. Okay, so what exactly do I have to do? What more information do I need here? Now, in order to move from the instantaneous rate of change to the proportional rate of change, which is k dot by k, I am dividing here, if you notice, by k, right? Basically, the idea is, let me motivate this with the help of an example, and I'll take an example from our day-to-day life. Let's take the case of prices. So, let's suppose that in the last 1 month, let's suppose our time period is the last 1 month, and in that 1 month, let's take two commodities. Let's say we have tomatoes and we have laptops. So, let's say the price of both tomatoes and laptops has increased by 100 rupees in the last 1 month. Tomatoes have been difficult. I've been really creating a lot of difficulty in terms of prices. So that's why I've taken the example of tomatoes. And the example that I have here is one where the price of both tomatoes and laptops has gone up by 100 rupees. Now, the question is, if I just take the absolute change in the prices, which in this case is 100 rupees, for both tomatoes and laptops, will that really convey anything? Because it's 100 rupees. So, here if we add some more information, which is, let's say, in the beginning of the month, the price of tomatoes was, let's say, 100 rupees per kilo. And now, because the change is 100, so it's now 200 rupees per kilo. So, that is the change that you have for the price of tomatoes. Basically, the prices have doubled. Whereas for laptops, let's say the price at the beginning of the month was, let's say, rupees 60,000. Now it has become, at the end of the month, 60,100. Now, you must also be thinking that there is a difference, because if we look at the change in the price relative to where we started, the two stories, in an absolute sense, the change in the price is 100. But if we take the change, the absolute change in price with respect to the initial price, the starting price, the two cases are telling you different stories. In the case of tomatoes, the prices have doubled, whereas for laptops, it's just a minute change in price. And this is where the idea of a percentage change comes in, which is probably how you calculated your rate of growth if you have done economics in high school or if you've done an introductory macroeconomics course. So anyway, the point here is whether you're looking at a percentage change or whether you're looking at K dot divided by K, the point is you're dividing by the initial value, and it is in that sense that we say it's a relative rate of change, because it's relative to this K that you have in the denominator. Okay. So, for instance, if K dot by K is equal to 0.05 per year or 5 by 100 per year, we say that the capital stock is growing at 5% per year. I hope the idea for proportional or relative rate of change is now clearer. Let us now connect things a little bit with what you are used to calculating, because you must be thinking of a rate of growth in terms of a percentage change. And now let's see if we can reconcile the definition that we are giving you here for a proportional rate of change as a rate of growth and what you are used to calculating as a percentage change. So, our definition of the rate of growth in terms of derivatives is K dot by K. The way to think about it is that when you look at growth rate as a percentage change, you look at the capital stock at time period T, subtract from that the capital stock in the previous time period T minus 1. So, basically the change in time that you're taking is 1 period, and then you divide it by the original capital stock, which is our starting point, K at T minus 1. So, actually, if I look at things in a discrete sense, now this is actually a little, I would like to just speak a little bit more about this, because what happens is that when we take a derivative, so when I'm talking of dk by dt, let me move back one slide, let me just motivate this discussion a little better than what I have done already. So the point is that when we have dk by dt, we are trying to incorporate really arbitrarily, really small changes in the independent variable, which is in this case t. So we want infinitesimally small change in the independent variable. But if you notice here, so when we want the limit of this expression as h tends to 0, so we have to get h to go to 0, but in practice, this is something which may not be easy to implement. It's not easy to implement infinitesimally small changes in the independent variable. In fact, in economics, the quantities that we deal with, such as prices or income, national income, these are usually, these are variables which are measured at intervals of days or weeks or months, or even you might even have quarterly data or annual data. So we are not dealing with we don't observe infinitesimally small changes in time, and what we have is discrete data. So in that sense, if I try and look at this expression K dot by K in a discrete sense, then actually I'm dealing with the change in the capital stock divided by time. And remember, the change in time is just 1 period here. So that T minus 1 will be 1. So I have the change in the capital stock in the numerator, and that will then be divided by the original capital stock in the denominator. So when I look at things in an average sense, not the instantaneous sense of the derivative, then my rate of growth, that the expression that I have here, can be written as K sub t minus K sub t minus 1 divided by K sub t minus 1. So for practical purposes, you will be calculating the growth rate as a percentage change. But yes, for analytical purposes where you have, theoretically you have continuity, you have continuous data, you have continuity in that variable, then you can, for analytical purposes, calculate the rate of growth as 1 by y dy by dt. Okay, so let's take an example and see how things work in practice. So let's, now here I've just made up some data. Let's suppose I have data for the capital stock for the years 2010, 2011 and 2012. Let's say it's for a particular state. And let's say the capital stock in 2010 was 10 rupees, let's say 10, or we can convert it into dollars. So let's say $10 million. In 2011, the capital stock was $10.4 million. So the percentage change here would be 10.4 minus 10 divided by 10 times 100. So that will be 0.4 divided by 10, which is 0.04 times 100, right? So that will be 4 by 4, that's a 4% change. Then for 2012, we have the capital stock as $9.8 million. So here we see that the capital stock has fallen, and in this case, if we calculate the percentage change, that will be 9.8 minus 10.4 divided by 10.4 times 100, which will then give you minus 5.77%. So you can see here that the growth rate can even be negative. Okay, so this is how you've actually been calculating growth rates, and what we are trying to tell you here is that the proportional rate of change given by y dot by y or k dot by k, whichever variable you're looking at, that is nothing but a rate of growth. So now what we're going to do is, I will take up this example. We will look at how this concept of a proportional rate of change applies to certain kinds of calculations. And we will derive two results where we can look at the proportional rate of change as we can calculate the proportional rate of change for the product of two functions or for a quotient, and that is something we will take up in the second part of this lecture. So with this, I conclude the first part of the lecture. Thank you.